Hello, I'm Robert Petrowski, and this is a thesis or project on the applications of computer vision and image recognition in architecture and construction. This is a topic that is of interest to me since I am in my final year of grad school in the MArch program. And the applications of data science to our profession is a pretty prevalent topic, especially in practice. So firms are now adopting new tools and techniques that call into question what architecture and design should become in the future. As it stands, school kind of, I don't know, they don't really attempt to address these changes and have pretty much stuck with traditional methods of design kind of philosophies. But the reality is that the profession is moving away towards them and more towards a business-centric and data-driven approach to managing projects as projects are getting more complex. So, this will be really hard to get under 15 minutes, but we'll try anyways. This thesis will examine how information communications technologies, particularly in the ICT industries, have overtaken architectural practice and building information modeling. This has produced a system of managerialism, which replaces, again, design and the traditional methods with an emphasis on pure economic rationality. And this is used through the use of tools that are aimed at increasing flexibility, communications, and data management. To address this issue, I will be investigating generative design, machine learning, neural networks, and image recognition tools, and try to apply them within Autodesk's kind of software packages that architectures typically use in the industry. Autodesk has released two kind of experimental platforms, DesignGraph and Project Dreamcatcher, which are machine learning applications to design challenges dealing with 3D geometry. And I think this is extremely interesting and maybe a different approach. So I'm going to examine kind of two different ways to go about this. So one of these is that DesignGraph is a way of generating kind of entire part assemblies in databases for comparison out of part and component catalogs. And to do this, I'm going to be looking into Google's TensorFlow as a method to try to learn, I guess, the basics or how to get, I don't know, a fundamental knowledge of kind of image recognition and retraining. I thought this would be the easiest course, so we'll see later that maybe is not the case, but upon researching it had kind of an established tool set in a set of tutorials that could allow for this. So, and then I'm going to be trying to apply kind of this data recognition or image recognition towards architectural elements in these design platforms, so that you'll be able to identify, say, like a column if it's modeled in either Revit or Rhino or Maya or Fusion or Inventor, any different software packages, even if it's a 2D line drawing or CAD-based thing, it could identify architectural elements, as I think that is the true, I guess, nature of what BIM wants to become, because right now BIM as a platform that is building information modeling is kind of doesn't take full advantage of the information part. I think that's partly due to its file types and the inflexibility that comes in transferring data from application to application. So, right as it stands, architecture and engineering are undergoing rapid changes. The profession is completely changing in its recent adoption of these building information modeling platforms. All firms of all sizes are trying to get into this, as it's becoming the only way now to do business within the profession. Clients increasingly call for it, and in some countries and in the European Union, it's even mandated for use on certain types of projects. So there's a very strong push towards this kind of platform on how buildings are to be done. And this is a very different approach from what has previously been done in, say, like a CAD-based platform where you design and draw out all your whole entire building. CAD could be, it's more open-ended. It could be called, say, a design platform. But building information modeling is strictly classified as an information communications technology product rather than a design tool, as the main focus of it is coordination with other fields and industries. And its goal is to streamline processes of managing and comprehending all the data that's associated to an entire built environment project. And this is done primarily through 3D digital representation of every component that is in that, project. So you're modeling all the columns, all the floors, all the windows. These all exist as separate kind of entities in a hierarchical platform called families, which are embedded into each, so different sets of information are embedded into geometries and then into a project model. So then when you say you need to do stuff like take project spec sheets or like tag stuff, all that data is in that model, and you can just call it through a simple command. So this is now being used as a baseline platform to save both time and money. The benefits are huge, but it's, I don't know, there's pushback in the regards that it's a business tool, and it's kind of downplaying the roles that design has, and the value design has towards people, environments, and communication. This has been kind of a push, and in, I guess, architectural theory, it's been labeled and classified as parametricism, which is a style coined by Patrick Schumacher, the head principal of Zaha Hadid's architecture firm now. And he's kind of arguing for architecture to stay distinctly he's arguing that architecture must adopt these data-driven approaches, must take on parametric solutions, utilize machine learning and business strategies that are more in line with different business and technology sectors that are the best examples of successful businesses nowadays. He believes architecture has to adapt to those conditions in order to create a proper dialogue and be able to address environmental concerns that are more in line with how things are done in today's fast-paced world, today's global connected world, to be more specific. So he has a bit fear that this kind of mentality, though, is not so much architecture but post-architecture. So if it goes too much into numbers, quantitative stuff, machine learning, it's going to not become architecture anymore. So he's arguing for architecture to be distinctly architecture. And if anyone knows architecture history, he kind of calls this a modernism part two, and he wants these elements to stay distinctly within architecture and architectural discourse and architectural education. I don't think that's going to be the case, but that's kind of the basis of what this kind of research is developed on. So, oh man, I'm going to go way over 15 minutes. I'm just looking at the countdown. So, Autodesk, which is the primary software company in the US that does industry standard software tools for architecture, movies, industrial design, civil engineering. They've kind of have a stranglehold on all these industries, but they're developing these tools. And more often, they're focusing their efforts on machine learning applications in their research department. And they're slowly implementing these into their more commercial packages. One of these is Design Graph, which is a different way of, I guess, managing large complex data sets, and it uses machine learning to kind of create a database of parts and relationships. So this is more used towards, I guess, engineering, mechanical engineering, industrial design, or applications that use a lot of standardized components that can easily be recognized. They kind of came at this with what if there was a better way to organize all information, so then it allows the designers to create more organically, for designs to emerge organically, so you don't get tied up in technical issues of representation and finding correct files and file types. So the core idea behind this was to use a Google search like function for 3D models. So standardized parts and assemblies in a firm's kind of like set would be organized, and then they would categorize every single component in design. And this would be done through classification, relationships between parts. So if you have like different like screws and what they connect to, different nuts, bolts, washers, all those types of things would, in the respective 3D models, could be called upon as entire assemblies. This would create a living catalog that would be able to react to constant change and evolving designs that go, because in these kinds of industries, there's a lot of iterative processes, a lot of changing, and you want your designs and systems to adapt to all these changes rather than, in a lot of cases nowadays, you just redo all the work. So this kind of software will find these relationships, and it's tied to the A360 platform, which is Autodesk's kind of cloud-based 3D model service. So then these products, these kind of components can be identified and filed based on shape, category, properties, pre-existing design conditions, where have they appeared before, and the computer will, or these machine learning algorithms will recognize, well, this shape is associated with this assembly, and these are your options for building or constructing this kind of design parameter. The other kind of project that is going full steam ahead is Project Dreamcatcher, which is more of a generative design platform. Again, it's an Autodesk research, I guess, project. And this allows CAD systems to generate and cycle through thousands of design options to meet a specified design goal. So this is different fundamentally, where designers kind of design. This allows the machine or the computer to design for thousands of conditions, and the designer will then be, his kind of role is to establish the parameters and goals that they want to achieve with this design. This could be anything from material constraints to form to load paths to thickness, all these various things, and then you have then you run the application and it will generate kind of mesh-based templates that solve for these scenarios. What's good with a mesh base is that it allows for a template where it can then be designed to reverse engineered with these other applications such as Inventor, SolidWorks, CATIA. All these things can then, you can redesign that to these conditions that could be, and then those platforms allow you to like simulate if it's manufacturable or not with today's tools. Okay, on to the project part. So seeing that this is a hot topic in the fields I'm interested in and the applications I use in work and in school, I decided to try to build my own really basic application of this kind of stuff with image recognition and apply it to these 3D platforms that I'm using. To do this, I chose Google's TensorFlow. It was pretty much it just came to mind in like searches as a tool that would allow for this without extensive groundwork and research into all these things, as it provides kind of base templates for image recognition and image database for training or model retraining. So I picked TensorFlow. It's Google's machine learning application. And it has unique features such as being able to provide visual representation through graphs and what's called the tensor board. So turning your multidimensional data arrays into kind of visual representations so you can more easily navigate and visualize how these processes are working. One of the benefits is that you can either use it for one or more CPU or on multiple GPUs. It can be run on desktops, servers, mobile devices, and all this is done through a single API. So though it was originally used for Google in developing machine learning applications and deep neural networks research. Since I'm running low on time, I'll kind of skip through this. So this is done kind of through, it's the same premise as the stuff we learned over the course of this class. Basic example of kind of this workflow or script is that you establish your training set and again the X and Y, the X training set and the Y kind of target values you're going for. This is done, TensorFlow uses what's called tensors, which is their version of these data arrays, and everything is stored as a node which can be used for this visual representation on the tensor graph, which would be kind of like this visual. Nodes can be anything from placeholders to constants to variables. Variables being the data that changes over the iterations. And it's very easy to produce, say, a simple linear model and create simple graphs. Just to follow kind of the outlines that we learned in class, this particular example uses linear regression as the loss model. From what I can tell, it's pretty similar in that it uses the sum of squares and it produces a value of loss. Being a high number means your variables are off and need to be adjusted on subsequent iterations. A loss of 0 would be your variables produce the perfect result. TensorFlow also utilizes optimizers, and in this case, again, it's gradient descent, which is the one we learned in class. Vastly simplified from what we did in the homework assignments, but there's a built-in, in the TF train, there's a built-in gradient descent optimizer. You set the tolerance, and then you set a train. And in TensorFlow, in order for it to calculate, you create a session that runs these particular functions. So a complete linear regression model for machine learning would be this kind of code. It uses the simple linear model that was above. It uses that same loss function, the same optimizer function. Training data is just a simple array of 4 numbers, and it will run the gradient descent kind of application we learned and evaluate the training accuracy. In this case, the loss is extremely low, meaning that it's fairly accurate. That's pretty dang close to 0. So I'm applying that's like the base way in how these TensorFlow applications will be set up. There's, again, a variety of different ways and functions to use, and different models to use. In this particular case, I'm using their built-in image recognition and retraining systems. This runs on Google's Inception version 3, which has been trained on ImageNet, which is an academic benchmark for computer vision. This is data taken from 2012, the Large Visual Recognition Challenge data. So Inception has already been pre-trained on this data set to recognize different things. Where this TensorFlow is useful is that it allows you to use Inception, its pre-trained data set, and alter only the top layer of training if you want to retrain. And this saves significant time. We're talking, in my case, an hour or 2 on my desktop to run a retrain application versus I think it was multiple weeks for the initial training on Inception. So, and that is kind of why, in interest of time, this was a great option, because it allowed for a quick retraining at the cost of super accurate results. So, as a default, Inception is pre-trained to identify certain things. I don't know what those things are, but in this case, Panda is one of them. So you send in an image of a panda, and it has identified panda with a score of 0.89, 1 being a perfect match, and it gives you the top 5 results. So in this kind of example, panda's by far the most, I guess, applicable. Giant panda, panda, panda bear, these kind of entries or labels were the most applicable to this picture. Custard apple also showed up, and so did Earth Star, but it gives you a kind of list, so then there's you can't establish if it's correct or not. In my case, I wanted to use this to find architectural elements within design platforms. And this is kind of my interpretation of a future application of BIM. BIM is kind of tied to its file type, which is the IFC file. And although it allows for building information, it's not cross-platform, meaning that file type only works within those specific applications. and any data associated with it can be accessed in all the other software. And in the case of buildings and built environment projects, you have hundreds of people, and in the case of complex projects, hundreds of different software tools that are being used. So it'd be extremely beneficial to be able to share this information cross-platform, cross-industry, so that everyone can be on the same page. Again, the goal of this BIM kind of platforms are for communication and flexibility, so you can identify risks or problems within these large complex projects. So I chose a steel I-beam image and ran it through the default inception model, and it came back with the best score as a tray, next best as a chest, and then file cabinet, trash can, mailbox. I guess it was attempting to identify it as a metallic object of that particular size, but as you can see, a steel I-beam was not part of this data set, and therefore Inception had trouble categorizing it as such. Luckily, Inception has that ability to retrain based on a new data set you create and only affect the top layer. So here I modeled various steel I-beams in different software platforms that are used in the industry. This is Fusion 360, Maya, Rhino, Grasshopper, and Revit. These would be my test images, much like the image above, and to see if it can identify an object based off, even if it's in different kind of design platforms. It should, since it's based off of 2D images. And that was kind of where this kind of research is going. Is this more of a 2D image approach? Is this image recognition for cross platforms? Do you have to convert these objects into printed 2D screen captures of the thing, or is it done through the 3D point cloud data? In the case of what I could, like in the example, I guess, computer code I can find, the 2D image was the way to go, since that is a lot easier to find information on. But in the case of like Autodesk's research, I believe it's the 3D route, where it's identifying three-dimensional data of a specific file type. Where file types kind of fail is that, again, like the IFC files for BIM, they are platform dependent, and you're getting categorization, but it's only going to appear through a particular file type and data structure. Using 2D, it kind of, I guess, breaks free from the constraints of one platform's file type. You can convert any software file to a 2D image. Usually there's a print screen function, usually there's an isolate and function where you can isolate your object and then export it out. Exporting out a 2D image even. So if that's the case, you can export out these visual representations, and then Inception, if trained on a data set of that particular architecture element, could be able to identify it. Problems being for this kind of method is that architectural elements, assemblies, these are all incredibly complex and involve lots and lots and lots of parts, and there's lots of different nuances. So having a general application like this might not work. And then, as I am well over 15 minutes, and everyone's eager for the results of this, I found out that using TensorFlow and Inception is also incredibly difficult, despite the documentation and GitHub and StackFlow kind of comments and tools. It's just like insane to go through all this stuff and figure out if everything's installed correctly. That, I think that was the biggest kind of challenge is installing all the different dependencies of TensorFlow, especially on the Linux platform, which I'm not too familiar with. A lot of these things had to be built from source or compiled from source. And since I'm very new to that, I have no idea if I did it right. So what I was able to do was, again, train on this, or identify on this untrained data set, but the retraining application kept turning up errors, such as directory not found, and I don't think it was properly rebuilding the retraining file. So the computer would go on for like 2 hours and then give me, like, it looks like a stream of code, but it wasn't able to execute that or do any I wasn't able to run any scripts using that compiled retrained model. So that's going to have to be just further research. I picked this as an easy solution, but again, it was a little complicated. But in theory, I think this method should work, at least in identifying very simple elements: columns, floor slabs, roofs, windows, doors, and you have a machine learning application that can be used cross-platform. I'm at double the time, so I think I'll stop here. Thank you, and yeah, hopefully I can keep working on this and get it working properly. It's kind of fun. Thanks.